So before we get started, I want to get your feedback on something. So, quite recently there was that there was like a student who was abducted in Auburn store, and you guys may have heard about her, and she was kidnapped and then later murdered. And so I was thinking of something like called a surveillance watch that people can use, and it would like monitor your environment and upload it to a cloud, your personal cloud. And it wouldn't be something that provides absolute safety, but it could provide some deterrence for other people who are thinking about, taking you or doing some harm to you. So here's some stats right here in the U.S. So this number of people, population about 327 million. Number of murders per year, quite large. Number of kidnappings, number of rapes. And it says here that 40% of homicides go unsolved. That's actually a huge improvement. Back in the 60s, it was 90% went unsolved. So getting better now. A lot of this has to do with a lot of surveillance cameras that are out there. Okay. But since like the 1980s, there's been 250,000, like 250,000 cold case files. So a lot of stuff that's out there. Here's the one issue that I was talking about, what happened to someone out here in Auburn. And you guys also may remember this one back from a couple of years ago. There was a jogger in Queens, and she was attacked. So here's the idea, right here. So you have to have a smartwatch. That's the problem. But this right here is this lens that I could possibly fabricate. They haven't made one this small before, but you may have seen large ones. It's called a fisheye lens. Has anyone heard of those? Yeah. So you're really familiar with these. So it's like a fisheye lens. So if one could be made really small, then it can just go over the lens opening of your camera. It could just be attached there somehow. But it would provide 180 degrees of imaging. There's actually some software that could take an image like this hemispherical image, and then flatten it back out. So it looks really, and you can't tell the difference. So it's really nice. So here's one idea, and so one idea is that it basically constantly uploads to your cloud storage, images that it's taking. So it's not video, but it's like still high-res images. It can do audio, GPS location, pulse rate, depending on what kind of sensors are in your watch. And so anyone wearing that is basically, here's a problem. Anyone wearing that is basically taking pictures all day long. So some people may consider that invasion of privacy, right? And I don't, because like when I go around, even through campus, I see cameras. There's cameras in this building. When you walk in this building, there are cameras. Have you guys heard of Google Glass? Yeah, those are still on sale.
Really?
Yeah. You can buy them on Amazon right now. And it was kind of interesting. So they came out a few years ago, and then Google stopped it for a couple of years, and then they reinvigorated it, and now they're back on sale again. Yeah. So, and people didn't like those, and I think the problem with those were that it was doing some facial recognition. So like strangers, it would tell you things about strangers, and people were concerned about that because, I don't know. Yeah, I just haven't heard any convincing arguments, but it's an issue. So So it's like a trade-off, you know, surveillance versus your right to privacy, right? And you could turn it off. I mean, it's sort of like the body cams that police wear, right?
Turn them off.
So, you know, if you're in your home, you know, you want to, you know, turn it off, whatever. But when you go out and about and you're out in public, people see you anyway, right? And in fact, the reason why people have to go to court and point people out is, you know, they're trying to use their memory, like, you know, yes, that person did it, you know, that type of thing. But if you have a surveillance camera, then that's a little different. I'm not sure if you actually have to, because it's not really you taking the camera, it's your device you're holding that actually took the picture. And so it's not like you have to identify anyone anymore, if that's the case. But, so, like, what are the issues with this? You guys have any issues that you can think of?
False alarms.
Yeah. From the
False alarms?
Last screen, yeah.
Yeah, that one, yeah, I didn't mention this verbally, but yeah, I was thinking about like maybe one mode if like there's like maybe there could be a mode where if there's a loud scream, then that can auto dial a call center. You guys don't like ADT, like so if there's like a glass break in your house, there's like a little microphone sensor that can sense if it's a glass break, and it can call the call center. And I don't know, maybe the call center could like listen in or get help, or I don't know. But it can't go directly 911. And for the reason for the false positive or the whatever it's called. But yeah, that doesn't have to be there. But yeah, that could be an issue. What else?
I'm still confused. Is this like something you would add on like onto like an Apple Watch?
Yeah.
Or something. Okay, so it's not
Yeah.
its own watch.
Yeah. So all it is this piece right here. That's to be fabricated, and then you have to upload an app, which is not even created yet. But someone has to make an app, and that app would constantly take pictures, record audio, and upload like once every few seconds to your cloud. So that's basic.
One of those tempered glass screen protectors you put on your phone, something like that, because over the whole watch, or just that.
Oh yeah, this little piece. That's an idea. Initially, I was thinking that this little piece, it just has some sticky stuff on it, but the sticky stuff can't like really degrade the image. So it has to be like, you know, some material will have to be maybe either tailor-made for it, or maybe there's something out there already. But
So this would go on top of an existing camera?
yeah, exactly. This little thing could go on even like your smart phone. It could be on your iPad, you know, a tablet. So, but if it's on the watch, so there'll be a little hump on the watch right there, where that lens is. So while you're walking around, and supposedly, if a bad guy can see your watch, then your watch saw the bad guy. That's supposed to be the idea. Yeah.
Does not have like a pretty adverse effect on like battery life because it's taking video like 24 hours a day.
Yes.
Yeah.
Yes, your battery life is going to be compromised. Yeah.
It's probably really hard pressed to get Apple to sign off on you letting them do that.
Well, this is something that you'll do regardless.
I know, but like you have to go through them to make an app for the watch, and they have
Oh,
to, like,
I
sign
see
off.
what you mean.
And
Okay.
They would probably never sign off on something
That's
like
interesting.
I don't think you.
I mean, Apple already does have the Find My iPhone feature, and it does have like a way that you could call 911 on your watch, like on the spot. So like, it might be hard to convince people to like ditch, you know, the traditional iCloud structure.
Yeah.
This thing takes pictures though, I think. Is that one? Because like if
This
someone,
one doesn't have a camera.
that's what I'm saying, like if someone went up and like grabbed you or something, someone could go into your cloud and see who it was versus like, that's like if you see them.
He's just saying the infrastructure's, there's something there already provided by a company that
Yeah.
has a lot of like
Yeah.
notoriety and trust, whereas if you just came out of the woodworks with a glass bubble and said, put this on your watch.
Oh yeah, no, I get it, I understand like, this is the.
It could be Android watch. It doesn't mean.
Yeah, it would work there.
Yeah.
You can do whatever you want on those.
Yeah.
I just had, is the purpose more to like solve the like murders and homicides that go unsolved, or is it more to protect them from?
Well, that's a good question. I think the goal is to prevent them from ever doing it. That's the goal. Because if enough of these are out, then, because the bad guy, if they know this is out, they'll be wondering, is that watch, one of these, surveillance type of apps, on that watch. And from a ways, it's hard to tell. I mean, if you look at the watch, then you can see there's a hump on it for the lens. But yeah, it's really for deterrence, because if someone, especially for kids, I was surprised by the number of kids that are kidnapped every year. In fact, a couple of months ago, I received an Amber Alert of a child that was kidnapped, and that child also was murdered as well out here. So that's the idea. So even if they take the watch off and then step on it and try to break it, at least they know, since it's uploaded, streamed to your cloud, they know who was it. Unless they're wearing your ski mask or something, but then everyone can see they're wearing a ski mask. And I don't think anyone wears ski masks out here in Alabama. It's gonna get that cold. Deterrent is the main thing. Yeah, you want to say something?
Do any current smartwatches have cameras on them? Because I know the Apple ones don't.
Yeah, they have. I was looking that up. They have watches. They have cameras. They have this really cool one that has how on some watches this little band turns around. They had a camera on it that turned around.
Oh,
so you can take pictures of selfies or of other people. Yeah. So not every watch has a camera, but the latest ones that are coming out, they do have cameras. And they have 5 megapixels to 8 megapixel cameras, so they're pretty good.
Yeah.
Yeah, high res. Any other issues?
I will just say, logistically, is this you mentioned children? I mean, I don't know how many parents give their children Apple Watches.
Yeah, no.
Or smartwatches. So
Yeah.
It seems more like a middle upper class solution.
Yeah, because you'd have to be able to afford the watch.
Yeah.
That's one thing. That is a problem right there.
I think it's good for college student types things, but
Mhm.
outside of kind of that area,
You can make a watch that
age
doesn't
range or
small times just starts
it's
emitting
not
signal.
middle class or higher than.
Yeah, exactly. And I was trying to keep this like this lens right here is going to be pennies. The app,
Well, I mean, it's
that
not
could be
connected
free.
to anything, it's just
But,
broadcasting signal, so.
But the cost is, can you afford some type of watch that can take pictures and can upload to a cloud?
But I mean, if you're looking more cost effective, would be a more good solution be like a black box where if it does detect motion for X amount of time, it starts emitting a signal?
You're not even big.
Then you'd have to go and trace down the signal with the.
Wait, say that again?
But it's like one watch.
It'd be like a watch that if it doesn't detect movement, it just starts emitting a signal for them to go track it down.
Oh, so instead of it constantly
Well, for a lower
uploading,
for a lower cost.
it waits for something worth taking a picture of,
Mhm.
right?
You
Yeah.
can either take a picture or start emitting just like a black box, where you can go trace it down just by just pinging.
Wait, so what do you mean by a black box?
It emits a periodic signal, so they can go try to find it if it falls in the water or the forest. You just don't the receiver. It's like a fox hunt type of thing.
Oh, okay. Yeah.
So that doesn't really stop it, but it just kind of
Yeah, they can at least, yeah.
recover the data. If you don't have a data plan, you just recover the data
Mhm.
up to the point.
Yeah, and for your other idea, if it could detect movement, because right now, on my phone, it'll put a square box or a square box or whatever around people's face, so it can identify faces. So if it took a picture and it can't identify a face on there, then maybe not upload that. But just because why take a picture of a dilly or whatever like that, right? That's not very useful. But yeah, so it can take pictures of faces. It'll identify faces and they'll send those pictures up. Only you can do that, something like that.
You could, I don't know if it would Right, you could almost maybe make it work out like a dash cam, or like it like records something and then like deletes it after like 30 minutes, flash nothing actually happening.
Yeah,
If
yeah.
something happens and then like press a button or something, like that's what easy.
Yeah, I was trying to do this 30-day thing, right? So whatever it uploads, there's a every person who has this has an app has a certain amount of memory allocated to only them, and maybe it's like a gigabyte. I don't know how many. I'm calculating how many how much memory it actually needs, but like it's only like the very last 30 days. So the next day comes in, the last day drops off, that kind of thing. Yeah, but I don't even know if 30 days is a good optimal thing. Typically, if you turn it missing, I think it's 48 hours is a thing. But if you've been stalked, or I don't know, like interacting with other people that may want to do you harm, they may need to go back a few days to see like what was going on up to that point. Something like I don't know. Is privacy invasion a really big problem with you guys?
Yeah.
For some people?
I think for this.
I mean, they're wiretaps people's homes now, so.
I mean, I just don't like the concept of. I think I would be cooler with it if the government told me what they were doing with some of these companies, like, because I honestly don't really. I mean, it is pretty twisted. Some of the stuff they make companies like Facebook and Google give them, but I feel like I'd prefer if they told me. They don't. So like something like this, they could just say to your company or whoever, if you don't let us have access to all these amazing pictures of literally like everywhere, if lots of people wore these, we're just gonna like tear your company down. And then they can do that.
But what if it's your personal cloud?
I mean, that I don't think the government cares. Right? They can get access to all that kind of stuff, right?
I don't know.
Like the NSA, they were like looking through people's texts. I mean, they still are. But that's like what Snowden and stuff was whistleblowing about. And it's like they can do that. I don't see why they wouldn't be able to just get access to all of this.
It was kind of like who's like basically hosting on that, right?
Yeah, and if it was any company that had a usable amount of server space for something like this, they're probably big enough that the government would be like, would have the
well, like at least have like a back door to get in.
Yeah,
because this could have like a double, triple pass code type of thing, but they would probably ask for a back door.
Yeah.
So what would be necessary for it to be okay with you? So is there like a middle ground?
Well, I guess this sort of thing isn't necessarily like, I don't think I'm the target audience, because safety isn't something that I like think about a lot. So if the risk reward for someone that this is a concern of theirs is my privacy is being violated, but I have some promise of safety, if that is okay to them, then go for it. But personally, I would only want the information to be sent to like maybe some remote like hard drive I have at my house or something like that. Never to a company.
I see. Yeah.
But I don't know. That's
so some home surveillance systems are like that.
Yeah.
Where like it's recording your home, but it's going to your own hard drive, and you can access it with your phone. Okay, that's interesting. Okay, so thanks for the feedback. It's very valuable feedback you guys gave. Okay, so let's get busy with today's stuff. So let's start off today by talking about some methods that we've been looking at to look at frequencies. And the reason why frequencies are really important, because when you're dealing with amplifiers, you want to know a lot about their frequency response and their ranges. So let's just quickly go over a few of the methods that we looked over so far. So remember this method, I forgot what lecture it was, but it was a few lectures ago, when here's some frequency response right here, and this has the characteristics that we're looking at, right? You're mostly concerned with the mid-band region right here. And so it's topped off here with a mid. And now you have these two frequencies for a cutoff. So you have this lower cutoff frequency and this higher cutoff frequency right here. Now you have these other poles and zeros along here. So remember, the zeros are when you turn up. So 0 here, 0 here. And the poles are when you turn down. So you're turning down here, you're turning down here, you're turning over here, you're turning down there. Okay, and remember, we can write this transfer function in terms of a polynomial for numerator, polynomial for denominator, and then break it up into different factors, right? Where you can factor out this a mid, this is constant. You have this low frequency component, that's a function of frequency, and high frequency component is also a function of frequency. And they're written like this. And so the idea of doing it this way is that, yeah, you can convert this style to this style and vice versa, right? But when you have it on this style right here, you want to look at your frequencies and make sure they're separated enough that you'll put your low frequencies, like these over here, will comprise this piece right there. And so that's where you get your zeros and your poles for this side. And then you have your mid-band region, and then over here, that'll be classified as your high frequencies, and then you write those like this. Okay? And the idea behind this is that here. Like if you were going to put these on a Bode plot, your A mid is like this. So here's your A mid, and that could be like at, I don't know, 13 decibels. Here's frequency, and for your high frequency, here's like 0 decibels. And that has, you know, amplitude of a max of 1, which is 0 decibels. So that's like this. And here's the one for your low frequency. Or this looks like this, where for high frequencies, it's like 1 or 0 decibels. Yeah, low frequencies, no decibels like that. Right? So this is at 0 decibels. So the thing is that you take this and you multiply it with that, and then you multiply that with that, and then you come up with this thing right here, which looks like this. Or, so, you know, something like this. And that's where you get this from, right? So that's where you have these components that asymptote to they're 1 for low frequencies here, and they're 1 for high frequencies there. And that's and you can easily see that and write it like this, right here. Okay. And so once you do that, then as long as the frequencies are separated far enough, then you can say that your low frequency right here, omega L, is, you can write it like this. So you multiply, or you sum all of your poles squared minus 2 times the sum of your 0 frequencies. The frequency of your zeros squared, right? And that will give you this. To get your high frequency cut off, it's 1 over the square root of those things. And these are 1 over that, and it's 2 times 1 over that. Okay, so that's one way of doing it. Okay. Does anyone have any questions about this method?
So it's just the approximation for time.
Hmm?
Those two, the approximations.
Yeah. These are both of these are approximations, and the better. Okay, the more separate your frequencies are, the better the approximations are. If you're, like for example, if these are like a decade apart from here to here, then it's a pretty good approximation. If it's less than a decade, then this curve right here starts interfering with this curve, and then they'll change where the cutoff is.
But the method we used yesterday was splitting out the constants, modifying the equations. Like we did yesterday, we were trying to determine the high frequency.
Oh yeah, yeah, exactly. So yeah, the method you're talking about like the dominant pole, right? Yeah, that's even an approximation of an approximation. So that's a worse approximation. Yeah. Yeah, but that's like a way just to get this straight. But of course, if you really want to do it accurately, the best way to do it is to get this thing right here, and if you knew it, and see, a lot of these methods right here are because the circuits are really complex, so that's why you have these approximation methods. If the circuit is not too complex, and then you know the equations exactly, then you plot it out, and then you just say, okay, here's my A mid right there, the height of that, what's 3 decibels down? And then you'll be able to find exactly where omega H is, and also where omega L is, by doing 3 decibels down from there. That's how to do it accurately, if you know that information. There's another method, right? And this is called the open circuit method, where remember, we're taking the capacitors and then looking at taking them away and then looking at the resistance and then making the other ones open circuits. Okay, so since we have 3 capacitors here, we have 3 types of circuits to look at, and then once you find the equivalent resistance seen from those where those capacitors were, through here and there, then you can find your frequency like this. And again, this is the high frequency. You can find your low frequencies too. Here's like an example for that, for low frequency. Now, but this method right here is the short circuit method, right? The short circuit method is very similar, except when you replace your capacitors, you make your other ones just short circuits. So this is short instead of open. But finding your low frequency and your high frequency is very similar. Like here, we want to find omega H, do that. We want to find omega L, do this. There. Another approximation method, though. Oh yeah, this method right here is also quite experimental too, right? Because some circuits, it can be really complicated, and then you could actually take some electronics and then probe that for the equivalent resistance and measure that capacitance right there. So that's an interesting way of doing it experimentally. If you have a very complicated circuit. Now for the review of our previous lecture, before the break, we went over the Miller effect, and basically the idea there is to find the equivalent capacitance, because for frequency, again, if you have the equivalent capacitance, then you could do something like this, where here's your equivalent capacitance, and then you have your equivalent resistance. That could be another approximation of your frequency. Okay. And again, remember what that was is, so how we did that, we had this RC type of circuit right here, and then what we did, we took this and added to that right here, this amplification unit that has some capacitance. And then what we wanted to do is take this capacitor right here and make an equivalent capacitor across it like that. That's easier to analyze. And then that equivalent capacitance right here is just that capacitance right here, 1 minus your amplification. Okay, and we can apply that to transistors, like what we did right here. So in this particular case, we have this capacitance C pi right here, 1 minus amplification. We have C mu, 1 minus amplification. This amplification, or this gain right here, is from base and emitter, so here to here, and this right here is from base and collector, here to here, across that. Now this has 0 gain from the base and the emitter, so that's why this C pi, it just stays C pi, and so you just have this, and this one stays, and that's like GM times R load. Okay, so today, summarize all this stuff. So we'll go over one type of thing, and then I'll show you a table that summarizes everything. Okay, so so this right here is a common source amplifier with unbiased source resistance, RS, and a small signal equivalent right here. And so what we're going to do is find the capacitance and resistance of that. And we're not going to include our pi, and then we're going to assume this RL are these two in parallel. So can you see how we went from here to here, right? So we have this capacitor right here. We have this piece right here went to the small signal model right there, and that's where we got these two from. And this became grounded, so that's why this D is in parallel with R3 over here. Okay, so this is what we get for the input gain between VG and I. So here's VG and VI right there. And so that's just voltage division. So that's where we get this expression from. And this other gain right here, GD, that's from VD and VG. So here's VG, here's VD right there. And this expression right here is actually from chapter 14. Okay, so we're going to just put that right there. This RL is actually these three guys in parallel right there. And this is quite large, so we could neglect that and just have RD and R3. And this RD right here, this is the differential mode input resistance. Okay, and with the Miller effect, so the equivalent capacitance is this right here. So we have this contribution for this capacitor, the GD, which is right here, and then this capacitance right here is the GS here. And these expressions right here, this is just from the last, like here. And we can take this and rewrite it like that. So if you take this, multiply by that, and add that, this term goes away. And so all you have left is just this over the denominator. Okay? And here's what we get for the equivalent resistance here. And that's just RG plus these two in parallel. And so if you take your equivalent capacitance, equivalent resistance, then you're able to get your frequency of your pole, which is this expression. You plug everything in right there. So that's just one example. The book goes through many other examples. So this right here is this one, but there's a common emitter, common source, and again, these are like the frequencies, 1 over your equivalent resistance and your total capacitance. So it's like that for all of these right here. Common emitter with an emitter resistor source, common source with a source resistor, common base, common gate, common collector, common drain. Okay, so you can use these to get the frequency of your poles. Okay. And see, with the couple of minutes I have left, were there any last minute questions on the exam we went over this weekend? I can pull it up real quick. Yeah, so in the first problem, that was just to explain the common mode rejection ratio. If anybody has a question, let me know. So for problem number 2, that was just to find out what are valid inputs and what are valid outputs. Number three is actually using problem number 2. Right? So you're supposed to find out if this is useful and why. That's for PMOS. Another one is for PMOS connected another way. Yes?
So you said that the difference between 3 and 4 is that the arrow is different on
yes.
PMOS. Would the difference in the arrow on number 4 make it an NMOS, or is it just a different kind of PMOS?
Oh, that's a good question. Yeah. I'll check on that. I forgot. There probably is. Yeah. Look at that. Number 5. That's to look at the input resistance. And there's a typo, but I corrected it here. And I also gave you guys the parameters and also the relevant equations, right? So if there's going to be a problem that requires you guys to use equations, I'm going to give it to you, at least the basic equations, and then you can figure out how to use them. But I'm not going to expect you guys to memorize all the formulas that we have to deal with. So that's just a variance. Yeah, you'll have to know this though. The hybrid pi model, that's very important in your area. Remember they were saying, like, even when you look up publications, the model there that they talk about most is a hybrid pi model. So you need to know that. Number 7. That has to do with the differential input resistance here. Put that. Number 8, Q point. Right, so you should be able to determine Q points of different things. And that's just basically the current and the voltage across here. How to determine those. Problem number 9. We were just looking at this. Yeah, so problem number 9 and 10, very similar to what we were looking at, right? So in this case, we're looking for the dominant pole. In this case right here, a little more complicated, and we had the A mid, we had the low frequency and the high frequency. And clearly here there's a big separation between the high frequencies, like the 400, 100, 200, and the low frequencies of 2 and 3. So those were grouped together for FL, and the high frequency ones were grouped together for FH. Right? So those numbers were chosen on purpose to be like that.
So we'd be able to return it pretty easily to test too.
Huh?
It'd be easy to see on the test too.
Oh yeah, if a problem like this was on the test, I would make the numbers far enough apart so you'd be able to tell what method is best to use for it. Yeah. Like on this problem right here, all the frequencies, they're all like within a magnitude from each other. So that's, that's pretty close. But here's like 292s between them. For this one, this is like the total capacitance using the Matthew effect. I mean the Matthew effect, the Miller effect. And the last one, yeah, we had lots of problems on this, right? So this is like one of our homeworks. We had to find the common gate, common source, common base. Oh yeah, and also during the homework, you had to figure out if they were useful or not too. They were hooked up the right way. So something like that maybe in the test. So any questions? All right, then I'll see you Wednesday for the